Okay, so our last way to change the activity of an enzyme is through inhibitors. So inhibitors are molecules that bind to an enzyme and cause it to lose activity. So for example, we have three different versions of this. We have competitive inhibition, non-competitive inhibition, and then lastly, irreversible inhibition. So let's start off with competitive inhibition. In this, the inhibitor, so the molecule that slows down our enzyme activity, is very structurally similar to our natural substrate. So let's orient ourselves to this little picture here. So we have our enzyme with an active site with our little pocket. And then our substrate in this case is a little oval. And then when you make the enzyme substrate complex, it will change shape slightly in order to start forming product, and then product will be released and you get the enzyme back as your catalyst. With a competitive inhibitor, that's what this I is, you see that part of this shape is the same as our substrate. So half of it's an oval, but the other half is a party hat. Looks like a party hat. So our party hat inhibitor can then bind to the same active site in a similar way, but it's not the correct molecule for the reaction to occur. So therefore, it will bind in the active site and then just sit there. No reaction will happen. So what this is saying here, when inhibitor binds, substrate can't. So it's kind of like, what's the game I was thinking of? It's a dumb little game. Where you play music and then you sit down and there's like one less seat. People are taking the seats of the substrate. So inhibitors are inhibiting substrate from being able to bind to your enzyme. So since the substrate cannot bind, there is no reaction happening, no product can occur. The way to fix this is you add a bunch more substrate. So now instead of 1-to-1 fighting, then there's maybe 10 substrates to one inhibitor. So you can outcompete the inhibitor for that active site and you get higher enzyme activity through that. You can also have non-competitive inhibition. So instead of competing for the same chair, you are competing for a different place. So what happens, we have this top is the same as the previous image, but now we have a different inhibitor. It's completely different from the substrate. And what it will do, it will bind to a different part of the enzyme and overall change the active site shape. So as you see here, with no inhibitor bound, we have kind of a hexagon shaped active site. But then when inhibitor binds, it changes the tertiary structure of your enzyme. It changes the overall shape of your enzyme and therefore changes what the active site looks like. So the inhibitor binds away from the active site and it causes a non-competitive inhibition. So it changes the binding of the substrate and does not allow substrate to bind. This is a little trickier in terms of it cannot be reversed by adding more substrate. Just adding more substrate is not going to help anything, right? Because you don't have the right shape to put more substrate into. The way to fix this is actually to remove the inhibitor. So you have to do some kind of chemical reaction to get that inhibitor off of the enzyme. And then last one, which I think is pretty cool, is irreversible inhibition. So it causes loss in all enzymatic activity, fully kills the enzyme. It's a form of covalent bonds. So these ones up here are all hydrogen bonding interactions, salt bridges, ionic charges, nothing covalent in our inhibitor. They're just binding in that active site. Our irreversible inhibition actually is forming a covalent bond with our enzyme. So it will bind to an amino acid. So I don't have a fun picture for this one. I just have a structure. This is the structure of penicillin. So specifically, I will point out this group over here, what I just circled, does change. There's a lot of different versions of this, but I just gave you a general one. The stuff on the end can change, and it changes activity just a little bit, depending on what you're trying to kill. So what happens with this? So penicillin is one of the first antibiotics to be developed. And what happens is this square next to a 5-membered ring, this core pops open really fast when it's reacted with. So this overall is pretty reactive. I'm not going to show you how because it's kind of complex, but this is a very reactive core, and it covalently bonds to amino acids in the cell walls. So this is an antibiotic. So in that infection or whatever is causing that infection, that virus, penicillin covalently bonds to the enzymes responsible for growing new cells. And when you get an infection, you get more and more and more growth of that like pus, nasty stuff, right? Those are more and more cells of the bacteria that you got in you or wherever it is. So penicillin then interrupts the enzyme that catalyzes the process to make more cell walls. So it inhibits cell wall growth and overall makes it so that the bacteria can no longer multiply or duplicate itself at all. I think this is a really cool molecule. There's a lot of rich history in this. It was developed, or it was found in the middle of, I believe it was the First World War. I could be wrong. If I'm wrong, I'll let you guys know. But it was developed in the First World War because in the trenches, in all of the different guerrilla warfare tactics, a lot of men in all of the countries really were getting really bad infections because there's moist, great environment for bacteria to grow. So a lot of men were not dying necessarily from the guerrilla warfare tactics, but more from getting infections. And they found this molecule kind of by happenstance. They were trying to find antibiotics. At this point, there were not any good antibiotics out there. And they found this bacteria that makes this particular molecule, and they figured out what it was and replicated that bacteria and made a bunch of it and ended up saving like hundreds of thousands of lives of troops during World War I. So this single molecule changed the outcome of the war. One of the first wars that we learn about in our history classes. This particular molecule changed the history of that. So I think it's really cool. Hopefully you guys think it's cool too.